Okay, so a quick nudge video on this problem with the car on the banked curve. I've got a picture here of, this would be like the car if it was coming directly at us. But what's difficult to picture here is, imagine a circular racetrack where the whole thing is banked. So it's a lot like a typical car racetrack, but those tend to maybe just be banked on the corners. This whole thing is circular. It's not an oval. And so what's really important here is to be able to picture the center of the circle, because the center of the circle would be like, if you could imagine the car leaving a little trail of where it was before, imagine a little smoke trail, half of a circle later it's going to be directly opposite where it is, way over here somewhere, and so it stays at this level, or this plane we might call it. So the center of the circle that it's making is actually like over here somewhere, not down here at the bottom of the what looks like a ramp. This is not really a ramp. So this is maybe the only problem you might ever see in your physics life, where the acceleration is not up and down the ramp, but directly across like this. So what that means is you are not going to do the traditional routine where you break everything into a parallel component and a perpendicular component. Instead, you're going to stick with the more traditional X and Y, or horizontal and vertical, if you want. That's going to be your coordinate system. So now the car is moving the fastest that it can without slipping off the track. And so if it goes a little bit faster, it would tend to slide like off the track. In this picture here, it would sort of like slide up this way. And so if we look at the forces, of course we have gravity straight down, and we have a normal force that's also angled like the ramp is. And the friction is keeping this from sliding up. So the friction is still perpendicular to the surfaces in contact, in this case down the plane. Okay? And this is static friction because it's not sliding, it's keeping it from sliding. All right? So again, a normal routine would be to take this gravity force and split it into two components so everything lines up. But in this case, we actually have to split up the normal and friction forces, because those are the ones that don't match the coordinate system we need to use. Because remember, our acceleration is, for a circularly moving object, the acceleration is towards the center. So that's the centripetal acceleration direction. Okay, so I'm going to draw in green here what these components would look like. Now they're going to run together a little bit. Actually, no, I think that's probably not a good idea. Let me just draw down here. Now, I don't draw cars very well, so I'm just going to draw a dot. And now I can represent these forces. I like to represent forces that I'm going to get rid of. I usually draw kind of lightly. So there's my normal force, but I'm going to replace it with an up component. So I might call that Fn cosine of theta. Here's my theta. That's that little angle like that matches this. And my, you could call it leftward or inward component of Fn times the sine of theta. Okay. Then I have my friction force, also going to be split up, so it's going kind of down this way, drawing it lightly. And it has components. I wish I'd have given myself a little bit more room, but here's its leftward component. Let's not get that mixed up with the component of the normal force. This is the friction force. Here again is this little angle theta, so this is a cosine for that one. And it has a downward component of Ff sine of theta. And then we still have, well, I didn't leave myself much room. We still have the gravity force. I'm going to draw it dark because it's not going to be split into components. And so I now have, if I imagine getting rid of these that I split up into components, I have 3 vertical forces and I have 2 horizontals. Now the 3 vertical forces are balancing each other because there is no acceleration in the vertical or y direction. So I can write a balance of forces equation. The upward component of the normal is balancing these 2 that go down. That's one Newton's second law equation that I could use. And then these 2 leftward components, or again we could call them inward or centripetal or radial, they all kind of mean the same thing here. Those 2 are what's allowing the acceleration. So that's more like F net equals ma. And within that a, remember, is the speed, because this is centripetal acceleration. And that's what we're looking for. One final thing before I let you take it from here. This is the maximum static friction they're being asked about. So this is one case where your static friction force can be expressed as mu times the normal force. Okay? I said most of the time you can't do that because it's less. But if you're asked for the maximum speed, we are using the maximum static friction. Okay, now the rest is a bit of a, it's kind of an algebra math, a system of equations kind of thing. I'll let you proceed with that. The solutions book in my room would be helpful for that too, but hopefully this kind of gets you started. Oh boy, that was over 6 minutes. Sorry about that.